we have a very distinguished set of panelists today. Professor Tamas Kerekes from Aalborg University and Professor Ioannis Krikis from University of Cyprus, both collaborators from the Painless project. And then the Windmill project will be represented by David, who graciously agreed to come on board in the last minute, since we had an unexpected departure of another panel member. So thank you, David, for that. The idea is to to discuss how all those aspects come into play, meaning machine learning, communications, and energy, all together in the context, of course, of these UAV-oriented networks that we've all been studying. And my approach, for this panel has been to, I'll provide first an overview of problems that we've been studying, optimization problems that we've been studying in the context of the Painless project, with which I'm more familiar. And then, I'll open it up to the panelists to make a few remarks. And then we take it from there. We can have a discussion, and hopefully people from the audience may be interested to participate as well. So, yeah, don't, as they say, don't don't go away after the break. All right.
Konstantinos.
Yes.
May I ask you a question? Since, like you say, I'm a late joiner of the panel, and therefore I'm trying to understand a bit more the emphasis. The topics you describe, does it have to be in the context of UAVs, or is it in the context of wireless networking in general?
No, it does not have to be in the context of UAVs. It will be mostly in that context because of the specific, scenarios that I will present from my side and maybe from the Painless side. But in fact, even some of those setups are quite general, and the UAVs become a specific aspect. The reason why UAVs make it much more interesting, in my view, is that you also need to take care of this energy autonomy. If you're going to be using very computationally and energy intensive techniques to keep those UAVs hovering in order to serve your users, you have to make sure that you achieve a reasonable trade-off. You don't use something that is, on one hand, too smart, but drains your battery within a few minutes. However, having said that, yeah, the topic is open to wireless networks overall.
Thank you.
Okay.
You're welcome.
Then let's continue the discussion in 35 minutes. Okay, see you back then.
Okay.
Bye.
Bye.
Jimmy, at the end of the day, you need to ask everyone to turn on the cameras for a picture, right? For our dissemination. It's very important, as Chris will tell you.
Yes, maybe we should have done it earlier then.
Yeah.
Maybe we should do it now.
Yes. So,
okay. So if everyone can turn on their cameras, we'll take a group. In fact, we need probably to, I see 2 panels, right? I only have 25 per screen. Jimmy, you will take the pictures, I guess, right?
Yes, I can.
All right. But it's good. Good to see you all. We should have had the cameras on earlier. Well, in most cases. All right. Excellent. I have a full screen of faces now.
Wonder how many rows we can have.
Yeah, I don't know if you can put them all in one. That would be, yeah, this is Zoom engineering. Okay, thank you all very much. Jimmy, let me know when you would like me to start.
Yes, you can go ahead and start now, I suppose.
Okay, so let me then share my screen.
Well, you don't have to turn off your cameras.
Well, in any case, I won't be watching you guys. All right. So can you all see my screen? Jim, is it okay?
Yes, it's fine.
Okay, excellent. And I want to, how do I get this? All right. Okay, so welcome to everyone. As we said earlier today, we'll end the day with this panel. Hopefully, you're not too tired already from the whole day, so we'll try to make it perhaps a little more interactive towards the end. And let me again thank Jimmy very much for organizing this and for putting together such a good program. And of course, both projects, the ESRs mostly, but the supervisors as well, for coming together in this very fruitful, I find, summer school. We have a lot in common, so it's great to have such events. And of course, many thanks to Thomas, Ioannis, and David for graciously agreeing to participate in this panel. So the panel is entitled, as you can see, Machine Learning, Communications and Energy Technologies, Synergies and Opportunities. And it's rather self-explanatory. We'd like to discuss or to pose perhaps questions on how those three areas intermingle, how they can help each other, and how far one can go in trying to push the boundary of optimal trade-offs depending on the different problems. Okay, so let's go ahead. Okay, this is an outline of my presentation. So basically, I've prepared a set of slides that are based on results derived in the Painless project. Since these are the ones that, of course, I'm more familiar with, but hopefully these will provide enough ground for steering the discussion from both groups. And also, of course, after I finish, I will give the floor to the three panelists to make their own observations and own statements regarding the everybody's individual angle on these problems. So the structure of what I will present, pretty much to trigger the discussion, is a number of presentation of a number of optimization problems that have been dealt with within the Painless project. This is by no means an exhaustive list. It's a few indicative problems that I found relevant to the theme of this panel. And then towards the end, a few thoughts and questions regarding the potential of machine learning. It's true that the two projects touch upon each other on the boundaries of UAV use for wireless communications, and I believe that Windmill is more heavily tilted towards the side of machine learning, whereas Painless is mostly tilted towards the incorporation of the energy aspect, both in terms of harvesting energy and in terms of being energy efficient. But of course, there is some machine learning taking place within Painless as well. So there is a lot of ground for interaction, I believe, and synergies. Okay, so going on to the next slide. This is a an overview of the Painless project. I mean, Chris did a very good job presenting in much more detail earlier this morning our project, but that's in a one slide summary, let's say, that comes from the beginning of the project itself. We even had this slide in the proposal, I believe. So Painless is about UAV assisted portable access points. We also call them aerial base stations, and the goal is to provide reliable connectivity, especially in cases where, such as disaster areas or special events, where you may not be well covered by the conventional wireless network infrastructure. So the big aspiration, similar to windmill, is to get rid of as much as possible, or take off rather from the grid, or be able to provide service when the power grid is not available. And one of the first things that one realizes once you go airborne, so to speak, is that you have to be careful about how you'll be able to power those aerial access points, for how long they'll be able to fly or to hover while providing service at the same time. And this is on top of all the other problems of being able to self-organize, to provide sufficient quality of service to the users, to backhaul to the fixed infrastructure, etc. So our big aspiration here, as you can see on the right lower part of this slide, was energy neutrality. I think that that's an overarching goal that, of course, we'd like to achieve in the context of future green ICT. But on the way to that, what we're trying to do in practice is to maximize the energy autonomy rather than being energy neutral. And of course, an important part of the project is harvesting energy via renewable sources. So this REB acronym that you see here stands for renewable energy base stations that use energy harvesting from either renewable source, could be solar, could be wind, etc. And in order to, one of the big also goals of the initial goals of the project was to define metrics that somehow take into account both the communication efficiency, or if you will, the spectral efficiency of this network, as well as the energy efficiency. And one of those metrics that we'll also see in a while is what we call the global energy efficiency. Okay, so the few problems that, or rather setups that I thought might be interesting to share with you today are the ones that you see here. So it's the first one comes mostly from the study group that looks at the modeling the energy consumption and the battery consumption and the energy harvesting, and has to do with how to optimize the battery consumption jointly with renewable energy harvesting, because in order to maximize this energy autonomy, you want to consume as little battery power as possible, and be able to make up the rest with renewable energy harvesting. So we'll see a few results there. Then we'll look at a more communication oriented effort that has to do with providing energy efficiency mostly on the side of the end terminal, and see how the different flying access points can cluster themselves in order to minimize the energy expenditure of the end user equipment terminals. That's from a study group within the project of ESRs that work mostly on the wireless communication aspect. Then the third one has a few, I'll show a few indicative results. It has to do with optimizing the trajectories, which, as David mentioned, is one of the first things you realize when you have UAVs and they move in three-dimensional space. It's very important to optimize the trajectories. And I'll show an evolutionary set of results where we start with a single UAV that is hovering at an arbitrary height, and we try to optimize this height. Then it moves in 3D space and it does both uplink and uplink, and we try to maximize the global energy efficiency. And then later on, we also look at some reinforcement learning approaches for this setup. And then finally, I'll also show some representative results from the area of hybrid antenna arrays, because as was also mentioned by several speakers earlier today, being able to have a directional antenna on this UAV, both for treating the users in the access segment, but also on the backhaul, as well as having the ability to tilt and all of that, to handle interference, etc., is also very important. And again, when you think of having all of that on board of a UAV, which may be rather light and may have certain battery power and capacity for harvesting energy, the thing may start becoming too heavy. And the question is, how do you find a good trade-off of an antenna array that can provide the required directivity, but without burdening too much the system in terms of energy needs, and of course of weight. Okay, so we start with the first setup. So this is a setup that comes out of the paper that you see here on the lower part, and it's this work is led by our project ASR Mashid Javid Sharifi, which is here today, and also supervised by Professor Kerekis, who will speak later. And the idea is that you have this is an indicative setup, let's say a baby setup that they considered, but of course it extends to much larger configurations where you have a master base station, and then this base station is the one that has access to both the grid, the power grid, but also it's connected to both a solar panel and some battery source for further power. And then it connects to two smaller base stations. So these are you can think of them as small cell access points who don't have the connectivity to the fixed power grid and rely solely on batteries and the solar panels for their energy. And of course, these could be the ones that are on board of some UAV, so they could be flying. And within this study group of the project, there has been a development, a rather detailed development of models for how energy is being generated, and using, for example, solar panels, and also models about how batteries, rechargeable batteries, are discharged and how their lifetime behaves, etc. So what the problem that was dealt with in the paper was a rather complex optimization problem, which is described in words here on the left. So it is to determine the power rating of the photovoltaic panels. By power rating, we mean to compute the maximum power for the PV panels and the battery capacity. So it's these two important parameters for the energy sources. And to do this both from a technical and from a financial, let's say, viewpoint, having in mind not only power autonomy but also the cost. And in cost, they count both the capital expenditure as well as the operational expenditure, so both capex and opex, and doing all of that in order to while trying to maximize the power autonomy of the whole system. So of course, we're not going to look at the details here of the math, but just to give you at a high level to show you what kind of expressions are used. So the cost, as you can see, in this case, is in the top right box, and it's the objective function here is to minimize the total cost, so capex plus opex, then power autonomy is captured via this other objective function that you can see here in the middle. And of course, there is the constraint when you have electricity demand and supply, that the two need to be balanced. And within the paper, there is a certain power dispatch strategy that is devised and is depicted by a logical diagram that is just shown indicatively on the right lower part of my slide. Okay, so if we go on to the next slide, what you see here is what was derived, what some indicative results of techniques that were developed for this multi-objective optimization. So a meta-heuristic algorithm has been explored within the paper that achieves Pareto optimality, and you can see here some results. So there were three different use cases. The one in red here is in Aalborg in Denmark. Then the other two in blue are in Malaga in Spain and Bourdur in Morocco. And you can see already that if you optimize, if you solve the first optimization problem in order to minimize the cost, that Denmark tends to be much more expensive than the Mediterranean here. So you can see that you achieve a 70% power autonomy with a cost of about $35,000, whereas you can achieve similar power autonomy in those more sunny regions with about almost 3 times less cost. Another thing that is also worth observing here is that you get diminishing returns after a certain point, which means that beyond 70% autonomy, your money pretty much goes to waste. You cannot achieve much better cost efficiency, let's say. Okay, so that shows that first of all, the technique works, and also it gives us some very important insights as to what would be a right balance in practice. Now, the chart you see on the right has a similar message. Now it's in terms of it also gives us the battery capacity and the peak photovoltaic power on the vertical axis on the right in red and blue respectively. And you can see again that beyond, let's say, 70% or so, the cost will explode, and also the power requirements will explode. So there's no point in going further. Okay, so the main message here is that with a meta-heuristic algorithm, one can get some very useful and insightful results as to how one should optimize the share of power. Now, let's go on to the next family of problems that was studied within the project. This is from another study group that was mostly about enabling techniques, and in fact mostly cellular clustering and resource allocation and communication techniques. And here the idea is that you have those two access points in green. This can be thought of as aerial access points, and each of them serves a number of UEs on the uplink direction. So this specific study is for the uplink direction. And what you want to do here is you want to form the cell boundaries of the access points. In other words, to position the access points and the corresponding and settle the corresponding power levels in ways that minimize the energy expenditure on the side of the user equipment of the mobile terminals that are served by them. And this is work done by two of our ESRs, Mahmoud Al-Aldin and Mohammed Al-Jarrah, in the project. And as I said, the context here is energy autonomous wireless networks, but it could be applied to other scenarios as well. The objective is to minimize the transmission power consumption per UE. And the approach that was taken is to look at it from two angles. The one is to optimize the user clustering, and the other one is to use assisted transmission of network coding type and routing in order to optimize this this power criterion. So for the optimization, they use the Voronoi tessellation for the clusters, and then once the clusters are formed, they use diversity gain and constructor interference to maximize the energy efficiency. And what you can see here on the right is an evolutionary graph of how the algorithm that they propose converges. So you can see on the left side, on the upper left side, you have a number of user terminals which are clustered in a certain way, and the cluster boundaries are the ones shown here with the dashed lines. And then after the algorithm converges, you can see that different clusters have been formed, and also the positions of the access points have moved. So the position of the access points have moved to the center of the suggested clusters. Okay, so this is again an indication that with this joint and decoupled approach, one can achieve important gains and make the system much more, let's say, energy efficient from the viewpoint, in this case, of the user equipment. Now, the next few slides have to do with the issue of placement, the one that was mentioned several times earlier today. So this work started with a very simple setup, the one that you see on the right part of the figure here, on the right part of the slide, where you have a single UAV that may hover in an arbitrary height. And what was studied, the intention was to try to see what is the optimal height if it serves a number of users. And this first study was done, I believe, only on the uplink direction. So it serves a number of users. These are assumed uniformly distributed in the two-dimensional ground plane. And then there's a certain power available at the access point that has to be used in order to serve all the users. And a line of sight model is assumed. In later works, this line of sight was also extended to include non-line of sight models as well. So the objective, as I mentioned earlier, trying to capture both the communication aspects and the energy efficiency aspects here, is what we call the global energy efficiency. So the global energy efficiency is basically the ratio between the total number of bits that are transmitted per hertz from the access point over the total energy that is consumed within the same time. So in other words, it represents total number of bits transmitted per joule of the total energy consumed. And this is work that was done by our ESR Nitin Babu. Later on, also extensions of this work, as you will see, in collaboration with several other ESRs within the project. So again, to formulate this problem in order to be able to optimize, to find the optimal height, you form these constraint optimization criteria. You want to maximize this global energy efficiency, and you have a number of constraints. You have some constraints related with the altitude, because there's a certain range of heights that you can accommodate, and you also want to guarantee a minimum quality of service towards all users. So this was captured here through a rate constraint. Okay, so it's a constraint optimization problem. One can try to solve it in a number of ways. What was solved in this, the approach that was taken in this first paper was using sequential convex programming, and the results that you get is what you see here. There is a as you can see, there is a sweet spot for the optimal height. So both the sequential convex programming algorithm and the monotonic function approach give a very similar optimal point. And the intuition behind this is that at a very low altitude, the global energy efficiency may be low because there is a very small coverage area. and then at a very high altitude, again, it may be low because the link, the range actually is long, and so it needs a lot of energy in order to try to reach the terminals. And basically, the optimal point is somewhere in between, where you manage a good trade-off between the two. So that was the first, let's say, result that we got with from this constraint optimization to see what's the optimal height if you move not really in 3D but along the vertical axis, and try to serve everyone with this single UAV. It's a limited scenario, but it was the first one that we looked at, and we got some interesting insight. Now, the second one, which is out of a collaboration of two of our ESRs, Nathan and Marco, who is also attending here today, I believe, is the case where you still have a single access point, but it may move now in proper 3D. And in fact, what it does is it uses a fly and hover protocol, if we can call it like that. So it starts at a given location, such as the location HP1 here on the right. In this location, it serves a number of users that are within its scope, and then it moves to a different location where it serves another set of users, and so forth. So it has this serve, fly, hover protocol in a sequential manner. And here both links. So we've been adding degrees of freedom. It can hover, and it can also communicate in both directions, both uplink and downlink. By the way, one thing I forgot to mention here is that one of the options, of course, in a realistic setup, when you have UAVs acting as access points, is that you may want to dock them as well. So the energy spent for hovering is by far much more, overwhelmingly more than what you use for communication, and that's important to keep in mind. Which means that sometimes a realistically efficient protocol may be one where you not just hover and serve, but you may actually dock and serve. So if there is a place such as a rooftop or a terrace, etc., where the UAV can dock, this can help a lot. And of course, at that point, it may be also able to refuel itself if there is a connection to the power grid. All right. So again, here an optimization problem was formed. This is about energy and cost-efficient 3D deployment now of the aerial access point. So it's mostly a positioning problem, and the metric from the communication viewpoint has been to maximize the data transfer in both directions from a set of UEs that are being served within clusters under the hovering UAV. So again, one formulates a constraint optimization problem. As you can see here, it becomes it's already quite more involved, and it has a number of constraints, and that corresponds to a mixed integer nonlinear fractional problem. That, of course, is very hard computationally, has exponential complexity. So then what our ESRs did is they tried to reduce it. So they reduced the problem and split it in two parts. So first in the vertical coordinates problem, so they solve that, and then once this is done, they use a multi-level circle packing to find the horizontal coordinates. Okay, so every time you break the problem in two like that, immediately you introduce some suboptimality, as we know from optimization. But again, it's a big question, and that's one of the things to discuss later on. How far do I want to go? I mean, if I get some decent solution with this suboptimal or slightly suboptimal approach, is it worth investing in something that may be several times more complex just to get a little better performance? And then it's not also a matter of whether it's worth doing it, is do I even have enough power budget to do so? So anyway, just to give you an idea, this optimization, this two-step optimization has yielded results. And in this case, I mean, you can see on the right for different cases of hovering power, what results one gets for uplink and downlink. So there is an optimal point where uplink and downlink data transfer coincide, and that in this case is the optimal point for transmission. And you can see here on the right the result of the placement in 3D after the optimization has taken place. So these are the 4 suggested points of hovering of the UAV in order to serve the users behind it. And what you see on the 2-dimensional ground is the corresponding cell areas that will be served. So again, we get some reasonably good, apparently, solution for the placement problem. Now, to take it one step further, and David mentioned that as well in his remarks towards the end of his talk, that one of the nice open fields to explore is the cooperation between robots and UAV. So in this case now, this is work from again 2 other ESRs, Igor and Nitin, and it's in the context of the proof of concept of the project. So here you have again a UAV that does a certain trajectory. So it's a single UAV that will be moving around and hovering around the serving area, but is being assisted by 2 robots, what you can see here on the left and on the right. And of course, this is done in a reinforcement learning context. So here, basically, the UAV, the drone, acts as an orchestrator, and those 2 robots act as learners, and the trajectory that the UAV follows is the one that allows the learning to take place, and of course inform back the agent in order to keep improving and optimize the whole trajectory. So the drone, as it says here, acts as an orchestrator and coordinates the transmissions and the learning schedule within a predetermined time frame. All right. So here there was this one was done with reinforcement learning. The cost function that was constructed has to do with the staleness of data. This represents in some sense a fair treatment of different UEs in terms of how long they wait until they get their data, how fresh their data are. And in the reinforcement learning optimization, this is an indicative path that may be followed, and the space has been discretized, and there's a number of it's been broken down into hexagonal cells, and the drone has 6 options, 6 choices for its next move every time. And as it keeps moving, the whole learning with the help of the 2 robots takes place. And you can see here on the right some of the parameters that are used for the optimization. So this is again a result from one of the papers that was written that came out of these pieces of work. And what you see here, the three red points here, the circle, the cross, and the star, and the star represent 3 different robots in this case. And on purpose, one of the 3 is a weak learner. Let's say it's one that is close to the edge of the cell, so it doesn't have a very good channel. It cannot learn very well, so it's actually a slow learner. And both what you see here is in blue the reinforcement learning trajectory, and in red the one done through the sequential convex program. And you can see that both approaches actually do go in the right direction. I mean, they get past the 2 fast learners quite fast, and they bypass them and go and spend more time towards the slow learner, realizing that he's the one that needs to be assisted more. And if you look at the paper, and you can find the paper on the Painless website, there's a certain quantification also of how efficient each of the 2 techniques is. the reinforcement learning technique is clearly, in most cases, more efficient, on the order of 30% or so. And at the same time, it can also address more complicated and more dynamic scenarios that would be harder to model and solve via convex programming. But again, the question is, how much, how worth is it taking this approach? And I have to say here that, what has not been done yet is to also make a comparison of those two approaches in terms of the actual, energy expenditure for doing this kind of learning, especially the online learning that is required. Okay, last but not least, it's on the topic of beamforming, as I mentioned earlier, that we would like, the access points to these flying access points to have, which, as I mentioned, could be useful both for the access point as well as for the backhaul point, as well as, depending on the setup, the peer-to-peer connectivity that one may have if the UAVs act as relays, etc., because it gives you better range, it gives you higher rate, and it gives you less interference typically if you steer it properly. But all this domain of beamforming through antenna arrays has been moving towards this massive regime where you need many antennas on the order of several tens or even hundreds in order to achieve very narrow beams. And of course, especially if you don't use millimeter wave and you use sub 6 gigahertz frequencies such as the ones that the Eurocom showed in their experiment, the size of this antenna may be large, but also the actual payload may be large, because each of those antenna elements may have may be quite heavy, having an entire RF chain or a phase shifter, etc. So what comes into play here is the concept of hybrid antenna arrays that have both active elements that do have an RF chain feed, but also passive elements that do not, and they can help actually shape much leaner and narrower beams without too much hardware, and hence without too much energy cost and without too much weight. All of those things come into play when you have them in a UAV. And so what we've been exploring here is, how can one design those systems? How can one optimize the parameters of such antenna arrays in order to have the desired beams? And I don't want to bore you too much with the details here, but it's a topic that we've been working most in the past in the domain of single RF hybrid antenna arrays. Now we're passing on to the multi-RF, so we can have a few active elements and several passive if you want to have quite narrow beams. And the mechanics of the problem are such that if you try to solve it analytically, you may get some closed-form solutions, but there's this coupling matrix model that you see here described in equation 1. But the problem is, if you try to obtain a closed-form solution with this closed-form solution may not necessarily lead to a realistic implementation. So you may get some values for the loads that make the whole thing, the whole array, radiate very poorly. So the radiation efficiency is not taken into account if you do this, and also the circuit stability is not taken into account. So you need some kind of to bring in those constraints of radiation efficiency and circuit stability into the problem. And there was a recent paper by another one of our ESRs, Mohammed Harun Tariq, who derived conditions for MAMPs, multi-active, multi-passive arrays, in order to satisfy this radiation efficiency constraint. But still, we don't have an algorithm. I mean, this is in the works for taking these constraints into account. So what the latest we have is an older algorithm that we had used, where again we have to decouple the problem into two sub-problems. So again, we become a little suboptimal. We have to compute the baseband weights first, so the ones of the parameter of the active antennas first, and then we fix those, we freeze them, and then we optimize to find the values of the analog loads, and we do this back and forth, this alternating optimization. And in doing so, you do get actually some very decent results. As you can see here, one can produce a beam with half as many active elements as in a conventional array. So that's important because especially in the context of a UAV, having half as many active elements may be close to having half the weight and half the energy expenditure of the analog feed part, and it achieves some good matching accuracy. But again, it's at the same time it's not the optimal solution. So the question arises once more: should we try to use something such as a machine learning technique that would give us perhaps 100% accuracy and achieving a global optimum, but at what cost to the whole system, both computationally and in terms of energy? So this was my presentation in terms of things that we are familiar with. We've been working on within the project to tackle, this all these joint problems where you have either the cost or the data efficiency as your driving performance metrics, but then you always have this this energy efficiency in the back as a constraint. And more than that, if you also harvest at the same time, it's not only energy efficiency, is what is the best way to harvest? How do I strike a good balance there? So the message so far is that several conventional, if I can call them like that, even though many of these algorithms are novel, but the conventional optimization approaches, often semi-analytic, do offer solutions, and those solutions have, let's say, reasonable complexities and reasonable performance. There are cases where, of course, you can do better, and the more complex the problem becomes, machine learning will probably be able to give you a one-size-fits-all kind of solution. But again, this will come at a certain cost, and we are still far from understanding sufficiently how much is this cost, and to be able to make some recommendations. But it's where we are. Hopefully, we'll do quite some more until the end of the project. But it's also this is a good place for this panel, a good place perhaps to discuss and hear opinions by everyone. So thank you very much for that, and for listening. With this, I will stop sharing, and I will pass the floor on to one of our panelists. Tamas, you want to go first?
Yeah, sure, I can. My name is Tamas Kerekes. I'm at Aalborg University. My background is in power electronics, mostly focusing on solar, wind turbines, storage, so everything related to electrical energy. And within this PAINLESS project, I'm supervising Mashid, and she is focusing on modeling this energy system, let's call it that way, where you have a base station which has a grid connection. Maybe it's off grid, it has some panels, it has some storage. So that's what we're optimizing. And well, it's actually an interesting topic with a lot of questions, and it's really complicated to find a solution, a simple solution, because well, parameters differ, and models need to be precise to do that. So that's what we're trying to do, and that's what we started in this optimization algorithm, to find at least some kind of path to show, okay, which way should you go? You need storage, then probably if you need a lot of autonomy, you also need to pay a lot of money. So you need to invest a lot of money into being self-sufficient. And definitely there's a lot more to improve on this task. And I think that's what we will do in the next year or so, which we still have back from the project. when I talk about machine learning, well, machine learning is not my core competence, but it is being used in energy systems. And here I'm not just talking about mobile base stations. Any load can be added, so it could be a residential house, it could be a commercial house. So nowadays, people invest a lot in being self-sufficient and making their own energy, which actually gives a lot of different case studies or study cases for here. I'm also always trying to focus on like a bigger picture. So it's the optimization can definitely be used in other applications. So not only UAVs and base stations. Yeah. I mean, I'm thinking what to say more about our work.
Thomas,
Yeah.
you had some slides. Do you want to share them, or it's up to you?
I can share those slides. Yeah, sure. Let me try to find them. I mean, those were mostly in general about energy modeling and then what is behind renewable energy. But sure, no problem. 2 seconds and I have it. Oh, and all of a sudden it disappears. Yeah. And I suppose you can see it now, right?
Yeah.
And again, as I say, I focus mostly on renewable energy, and one of the most or the fastest growing energy solutions is PV, and this has been seen during the last decade, and it's also one of the cheapest solutions if we look at the cost of energy production, and it's actually even cheaper than wind turbines. And as you can see, during the last decade or 2 decades, a lot of PV was installed, and it's reaching several hundreds of gigawatts. Such PV systems are installed mostly for commercial and high power energy production. But also residential systems are preferred connected to the grid or off grid, depending on location. So it can be mentioned that PV is becoming a huge market, and it is increasing. China has been installing a lot of PV throughout the last 5 years, which actually makes sense because a lot of the panels are produced in China, so why not use that? And they also need energy more and more, or what I want to say is that the energy need is increasing every year. The only problem with renewable, and in this, when I say renewable, I mean solar and wind, is that power production depends on weather conditions, and as you can see on this slide, the right bottom 2 slides show that solar production is available when the sun is shining, which means that you could have a surplus of energy which is stored in some kind of storage. Mostly it is batteries that are used in combination with PV or wind production, and then it can be used later for supplying the loads when there's no sunshine or when there's no wind. So This means that hybrid power plants, and by hybrid I mean combining different renewable energy sources with storage, is a must if we want to have if you want to reach the goals, European goals, Danish goals, whatever those are, about green a green future. And if I go to the next slide, well, this electrical energy needs to be converted. And if we talk about PV, well, PV systems are really nice from the point of view that they don't have any moving parts, which means that it's cheap to maintain. On the other hand, they deliver DC, so they deliver direct current depending on the power from the sun. So depending on sunshine. So it means that you have your PV panels and you have your PV converter supplying energy to whatever grid you have. With wind turbines, the generator is actually generating a varying frequency AC alternating current, which means you need a different converter type to, again, to connect to the grid and feed or inject the energy to the grid. And then again, also storage solution comes in combination to these systems, and you need another converter to do that. And you want to charge your electrical car, which means depending on the type of electrical car you have, again, a different converter needs to be used, especially if you want to use supercharging at very high power levels. This means that you have a lot of different converters connected to the different sources, and it's an expensive thing, and it's also wasteful because you're not using it to its full capacity, because sunshine is during daily hours, right? And during the night, the PV converter is offline, it's doing nothing. Again, the wind turbine is working when there's wind. The storage converter is working when it's needed to supply energy, and again, the electric car is charged when you get home, probably from 5 to the morning. So you have a lot of power electronics in here which are not used all the time, so that's why it's expensive and wasteful. So our proposed solution, and this is actually one of the research projects that we are working on, was to use a converter that can combine all these sources in a smart way. And it also has integrated batteries. So in a way, this converter is in charge of all the energy production, storing of the energy, balancing the energy, and using it in it would definitely, it could be like a microgrid. So this could even support the grid with ancillary services. There could be blackouts, or there could be events on the grid, faults on the grid, during which nowadays renewable energy systems are required to support the grid with reactive power, active power for frequency support. So this can be done by power electronics. So why not use it to the fullest? So yeah, that's what I had on the energy combination, balancing different renewable energy sources, storage, and yeah, the power of the future.
Thank you very much, Thomas.
Sure.
A quick question: this super converter that they're talking about. So is there a plan to build it? Or
Yeah.
to build a prototype?
Actually, we've built a prototype in the lab, and when I say prototype, is a few. Maybe I can find a slide, a picture of the system, and we're now building a second prototype, which is an in-house solution, should be more compact. The only thing is that with which we didn't count was a shortage of components. And last week I've ordered some PCBs, and some components from Texas Instruments are not available until December. So actually we're kind of in a problem to see what we can do. But sure, I can actually find a slide or two. But again, it's a 1 kilowatt system, like low power. What we can use in the lab.
And the idea is for the converter itself to be.
I mean, the thing is that these different systems or different renewable sources have different voltage levels, which means that this converter is a so-called multi-level converter, where you have different cells connected in series, which can actually reconfigure themselves to different voltage levels. This means that they can connect to the grid and supply some power, but they can also connect to a lower voltage, let's say electric car or a PV system, which this also means that you only need one converter for your house or for your application. This could also be used for wind turbines. In case of offshore wind turbines, you actually have a diesel generator on the platform, which should supply energy in case the onshore cable has a fault. This also means that you have a renewable energy system which is running on fumes during certain cases, because you need to make sure that this turbine is controlled and has energy during these off-grid parts. But it's
and
really
Thomas, sorry to
yes.
interrupt you.
Yeah.
I mean, another very perhaps silly question. I mean, usually when you have multi-purpose devices, they tend to be more expensive, than the single-purpose device, right? So in cases
Yes.
where you may not need to have multiple sources, will it be able to replace them all? I mean,
No, it wouldn't be able to replace one single converter, because you have more components, which means you have it's a much higher cost. It's
so
much
then
more
the follow-up
complex.
question is, could you guess, do you have an estimate of what percentage of use cases will need to harvest from more than one sources, I guess? I mean,
That's a good question, and if we think of maybe nowadays, right now, it's not a good idea for residential, because in most cases people just have some PV on their roof. They don't have storage included, because whatever surplus of energy they have can be dumped on the grid. Nevertheless, that's not a good economic choice, because you don't, at least in Denmark, you don't get paid if you produce energy and you don't use it yourself, which means that actually it makes sense to have storage. Now, if you already have storage, then it also makes sense to support the grid during. I mean, the price of the energy is fluctuating during the day by the hour, and okay, maybe on the residential scale this is not a good solution, but actually Vestas had 10 years ago they built a 1 megawatt battery container, which they've just used for balancing, and it was a profitable solution. In Italy, they have these pumped hydro system, which during the night is pumping water back into the container by the cheap French atomic energy. And during the day, during the peak hours, it's delivering power to the network. So storage solutions, being that different storage technologies combined with renewable energy, is a viable solution. And as you say, not always, but in certain specific cases it is.
And also I'm thinking, to bring it a little closer to, to the UAV concept. I mean, if one could have such a universal, let's say, converter on a flying or on a portable rather access point, be it flying or non-flying, but portable, that has a lot of financial value too, because
yes.
you know, if you're going to be using this for, let's say, remote areas or poor areas, etc., and you can have a unique, a universal design that will harvest whatever is needed without needing to tweak it. This may be interesting, right?
I mean, the advantage of this topology is that it could connect to the grid, or it could connect to one PV panel, depending on how fast it needs to charge. So if it's on a UAV, it could actually just choose where to connect to.
Or to a wind
turbine.
Yes,
definitely. And to a wind, then it's an AC. So connecting to an AC source, it needs a different type of converter. But just because this converter can be, and maybe I can share now my screen because I found the slide. Just connecting to, I mean, I'll try to zoom in so then I can see what I'm showing, and I can also see you guys. You have these submodules which are connected in series, but these submodules can be bypassed individually depending on how they are connected. So this means that you could have, well, this is a specific case for residential, but you could actually configure the voltage level by bypassing or connecting different submodules in series. And yes, it's more complex because in case of a simple PV system, you only have 4 switches, and those switches are, okay, they might be higher voltage level, rated for higher voltage. In this case, you don't need to rate them to high voltage because they are connected in series. So from a cost perspective, yeah, it's a lot of variables. So it's not a one-way solution, but it's definitely more complicated, more expensive than one single converter.
Okay,
and,
thank you, Tamas. Thanks a lot. Perhaps we can move on to Yanis. Yanis, from a completely different perspective, I think, has a few remarks to make.
Yeah, thanks. So let me also share my screen. Okay, so yeah, I mean, the presentation is a little different from Tamas. It's about wireless power communication, which of course is a component of Painless project. As you will see, is a technology where energy, communication, and very recently machine learning coexist and collaborate. So let me start with a very brief introduction to this technology. So as we know, in conventional wireless technology, we have nodes or sensor or devices with a limited battery lifetime. And it's obvious that in order to maintain operability, a battery replacement and recharging is required. However, this classical process in some cases is infeasible. Think, for example, sensors implanted in medical devices or embedded in buildings or used it in chemical environments, or in other cases, this process is very costly. For example, Internet of Things application, where we have a huge number of devices. Also, the cost for the battery disposal becomes very critical. In this figure, you can see the number of connections with time, and as you can see, there is exponential growth. Specifically, from 5 billion phones in 2017, we will have around some trillions of Internet of Things connections by 2035. So the energy sustainability of these devices becomes a very critical issue. A powerful solution to this problem is the technology which is called wireless energy harvesting, where the nodes can be charged from the ambient, from the surrounding electromagnetic radiation. And currently there is a lot of interest in this technology, mainly for 2 main reasons. The first one is that due to the progress of electronics and signal processing, the power requirements of devices becomes very low. For example, we can find in the market sensors that operate with only 10 microwatt of power. The second reason is that there is an exponential growth of wireless technologies. From classical TV and radio in the previous decades, we have, several, let's say, cellular generation, Wi-Fi, and so on. So the ambient electromagnetic radiation increase and probably is able to support these low power devices. In this figure, you can see the Cummey law, so as the computation per microjoule with the here. And as you can see here, for a constant computation load, the power requirement of the devices decreased by factor 2 every 1.5 years. This means that in the future, we are going to very low power devices that can be operated by the ambient electromagnetic radiation. However, this technology has a drawback. Normally, it's unreliable, unpredictable, and therefore cannot be used for applications with very strict quality of service constraints. Therefore, we have another technology which is called wireless power transfer, WPT, where the nodes charge their batteries from a dedicated for a fully controlled electromagnetic field. So here, as you can see, there is a transmitter, let's say, that broadcasts electromagnetic radiation or generate an electromagnetic field and distribute devices that harvest this energy. So in contrast to the ambient to electromagnetic energy harvesting, here the process is continuous, is stable, and fully controlled. Therefore, can be applied, can be used for applications with more strict quality of service constraints. This technology can be realized with three techniques: inductive coupling, magnetic resonance, and electromagnetic radiations. The first two are very efficient, but are near field, work only for very short distances. On the other hand, electromagnetic radiation allows us to achieve longer distances. So in this discussion, I mainly focus on the electromagnetic wireless power transfer. So in order to achieve wireless power transfer with this technology, we need antennas, of course, antennas to broadcast electromagnetic waves, and also antennas to receive the electromagnetic waves, and rectennas, I mean rectification circuits, to convert the RF to DC power. Electromagnetic wireless power transfer provides also a lot of positive characteristics. First of all, long range. Small form factor. So this technology, since it's just an antenna, can be easily integrated into your mobile phones, for example, or in small sensors, in comparison to inductive coupling, where normally you need space in order to locate the coils. Flexibility, multicasting, can support also mobility, environments with line of sight, but non-line of sight as well. And of course, easy implementation in wireless communication systems, where by default, we have electromagnetic waves. But also we have some issues, some drawbacks. First of all, low efficiency, specifically due to path loss, which is the key bottleneck in this technology. Also, we have safety issues, radiation issues, since we propagate, we transmit electromagnetic waves. Currently, there is a lot of interest on this technology, also from industrial standardization process point of view. I would like to mention here Airful RF standard, which is the key activity in the standardization of electromagnetic wireless power transfer. Key applications of interest: wireless sensor networks, consumer electronics, Internet of Things, RFID tags, and so on. In wireless power transfer, we don't have information. It's just a technology known from 70s, where we try just to transmit energy. The integration of this technology in wireless communications result in a coexistence of information and energy flows. So RF is used in order to convey energy, information, or both. And exactly this coexistence generates a new communication paradigm, which is called wireless powered communications. Here you can see a general system model, general structure of a wireless power communication system. As you can see here, we have an access point which broadcasts information and energy in the downlink, and devices, distributed devices, that harvest these energies and use it in order to power the uplink channel. Of course, this is a very general structure. This structure appears in the literature with more specific network architecture, such as, for example, the wireless power communication network, where information and energy in the downlink are transmitted in orthogonal channels, or simultaneous wireless information and power transfer, where information and energy coexist in the same waveform, and other different and various network architectures. Wireless power communication is one of the key, let's say, research activities of my research lab at the University of Cyprus. We study the problem from a different perspective, from different layers. First of all, we study the problem from a fundamental perspective using tools from information theory. We try to characterize and understand the fundamental information and energy trade-off. It's called information energy capacity region, since the same design cannot maximize both information transfer and energy transfer simultaneously. We study different network topologies, MAC channel, broadcast, relay channel. We study also the associated input distribution and so on. So here is the basis in order to understand this technology. Then we move to the link layer, to the link level, where we try to design waveforms, modulations, precoding schemes, transceiver architectures for this technology. The basic tools that actually we use here is signal processing and optimization theory. Then we study the problem from the system level, from a macroscopic point of view, where we can model the randomness of the location of the base station of the users. We can model multi-user interference more correctly. So in this way, we mainly use stochastic geometry and probability theory and different aspects of communication systems, 5G, machine type communication, cellular, and so on. And finally, we study the problem from implementation perspective, just some ideas that are developed in theory. We try also to have a proof of concept, a demo, mainly with expertise on software-defined radio, but also in collaboration with other people working on RF and antenna engineering. Wireless power communication, I still believe that is an enabling technology for the upcoming 6G communication systems. First of all, is the technology where information and energy coexist, co-designed, co-engineered, is an enabling technology, built-in block for upcoming 6G wireless technology. I recall you that one of the goals of 6G is the massive connectivity. We talk about 10 million devices per square kilometer. So it seems that this is very critical in order to maintain the energy sustainability of the network. And my personal vision is that we try to design a telecom network, which at the same time will be an energy provider. Here you can see this network. You can see some base stations that operate in the classical communication mode. Other base stations just transmit energy, operate as power beacon. And other base stations do both in a dual mode, transmit information and energy simultaneously. It seems that communication and energy are just two extremes in a network where wireless information and power transfer coexist. Just two extremes. Let me finish, with some ideas about machine learning in wireless power communication. As I strongly believe that there are a lot of opportunities about machine learning in wireless power communication. Here, just I mention three potential directions. The first one is machine learning could be a new design methodology for wireless power communications. Currently, we use this classical model and optimize approach. So we have some mathematical models for a rectenna, and we use some tools from signal processing or optimization theory in order to solve the problem. But here, the key problem is that the mathematical model of rectenna are not accurate. The mathematical models that we have in the area are too simplistic, do not take into account some hardware nonlinearities, such as impedance mismatching, parasitic phenomena, frequency demodulation products, and so on. This is the reason that there are some opportunities for machine learning here. For example, we can optimize the transmit and the receiver without intermediate blocks, without models. A typical example here is autoencoder, where we can replace the transmitter and the receiver with deep neural networks. Another direction for machine learning is that it's a tool, it's a mathematical tool to solve complicated optimization problems that we have in wireless power communication. And the problems are complicated because the wireless power transfer is a non-linear process. So the problems that normally we face are very complex, non-convex, and with this tool, we can probably learn some parameters, extract some parameters from the problem, and then we can solve some problems with less parameters, with simpler structure, and so on. So this combination of model-based optimization and machine learning could be a very interesting direction for wireless power communications. The third direction and opportunity that I can see is that wireless power communication could be an enabler also for machine learning algorithms. Here, just I mentioned one example that currently I'm working is wireless power communications with federated learning. So here you have an edge server, which is, and here you have the local, let's say, devices. We have the access point here, which in the downlink broadcast, the aggregate weight, the aggregate model, but also energy. The energy is used by the devices in order to process, the local data and also transmit the local weights to the transmitter. So this is just an example to see that wireless power communication could be an enabler for machine learning algorithms in general. Just to conclude, I believe that machine learning obviously is a very interesting tool. We have these two extremes here, model and optimize, learning from our side. The first technique is very sensitive to the models. Also, the algorithms sometimes are not computationally are not possible. But the very positive thing here in the first approach is that we can have an intuition about the solution. On the other hand, learning sometimes, of course, work very well. But most of the cases also, I believe that we have a lack of performance guarantee. We have also lack of human interpretability of intuition. So I believe that the combination of those two techniques seems to be a very interesting direction. So model and optimize, learning from one side, to have, let's say, an integrated design approach for wireless power communication. Probably this is a global, observation can be applied to many other problems. So this is the statement from my side, Constantinos.
Yanni, thank you very much. Excellent points, an excellent, array of topics here. I very much like this view of this holistic view where you have energy on one side and communication on the other, and in fact, it's a continuum in between to be bridged in future networks. My observation would be that I would probably throw in, renewable energies beyond radio harvesting as well, because that's part of the continuum as well. The networks do not operate in standalone fashion away from the wind and the sun. So perhaps that should be thrown in as well, and try to bridge also a little bit between your world and the world of Tamas. Yeah, and maybe since I know we only have another 12 minutes, maybe we should pass on to David to make some remarks, unless Yanni, you wanted to say something before.
Yeah, let's proceed with the demos. Sure.
Yes, thank you very much. David, you're a little last but not least, but please, the floor is yours. But you seem to be muted though.
Yeah, thank you, Constantinos. In the meantime, I did prepare just a couple of slides, but given there's little time, I will make it really short.
Okay, great.
I'm trying to share, but it's one of these cases where somehow I can't find my I can't find the PowerPoint presentation in the. Okay, let me try again.
Yeah, no problem. So Yanni, meanwhile, do you agree with my point that we should probably not divorce from the classic renewable sources when we talk about radio harvesting?
Yeah, Constantina, I believe that wireless power transfer is not applied to any scenarios. It depends. It's a complementary technology. It's applied mainly for very low power devices. Wireless power transfer, energy harvesting, and classical, let's say, solutions is always there and can be combined with wireless power transfer. For example, there are also some solutions where the device harvests energy from solar and convert it to RF for some specific application. But again, I would like to emphasize that it's a complementary technology. It's not a solution of everything.
Yeah. Thank you. David, we can see your screen.
Okay, thanks. Yeah, I was not able to share the PowerPoint application, but so I was able to share my entire screen. Okay, so I'm not expert at all in the area of smart grids, and I have little to comment on that specific domain. But because the panel is supposed to also talk about machine learning, I want to talk about an idea, a concept that could be seen as a tool to solve a number of scenarios, and including energy optimization scenarios. And basically, it starts from the premise that in many networks that people talk about, and smart grid is one kind of network, swarms of UAV is another kind of networks, wireless networks is another kind of network. In many types of networks, there's a need to optimize the system in a way that's distributed. That means that you would like the elements of the network to sort of coordinate the actions such that the network as a whole can perform better. So, you know, it is like football players working together as a team. The problem is that in many networks, the way you will coordinate the action of those elements is only possible if the players, the elements of the network, can centralize their decision, which is not always possible, especially for big networks. So it's a little bit like if you had those kids trying to play football together and score the goal. They have a common objective, but somehow they are all blindfolded. And you can imagine it's much more difficult to pass the ball to each other now. So it's a little bit like playing together, but under uncertainties. So this, as I was saying, this could be an enabling tool in a number of cases where machine learning has something to offer. There's really a lot of scenarios that we have been talking about here in my group. So, for example, robotic games, swarms of UAV that need to coordinate their actions for, let's say, whatever objective, maybe coverage or search and rescue. Cars arriving at a crossroad and that need to determine a priority between themselves. Robots in a factory that need to cooperate to achieve a certain task. And of course, radio equipments in a network that need to coordinate, and because otherwise they would interfere. So in the common aspect behind all these scenarios is the fact that in each case, there's no optical fiber that connects every one of these nodes to each other. So those little nodes have to come up with decisions that make sense for the entire network, while not exactly knowing what the other nodes are doing and what is the data that they are observing. So it's called asymmetric uncertainties. So, for example, I might be one of these nodes, and maybe my sensors have a high quality. I know a lot of things about what's going on. And then maybe you, Constantinos, you are a cheaper node, and your sensors are very bad, and therefore you have a more restricted view of what's going on. And still, we need to come up with decisions that is consistent with each other. So what to do? This is an example with the car crossing scenario, because it's actually quite meaningful. Imagine that you have two cars arriving at the crossroads. They are autonomous, and they need to determine the priority rule. We want something that is not centralized, so just based on local sensors. Maybe the blue car is an expensive, high-end, whatever, BMW, and the green car is a cheaper car, maybe a small French car. So the sensors are not as expensive, and its view over the system is a bit more limited. So now what do? You need to decide at each car if you're going to accelerate or break down. So you need to come up with the best joint decision such that all cars end up passing through the crossroad with the smallest possible crash probability. Okay, so you need to find a policy. And that's not actually trivial at all. Like if you are in the expensive car, you know in principle that the other car, I mean, you could know that the other car is a cheaper car. So you know it operates more blindly than you are. And the cheaper car might know that the other car is an expensive car that has more knowledge. Okay, but what do you do with it? I mean, if you want a cheaper car, are you going to say, okay, I have the cheap car, so therefore I should just slow down and be more cautious and let the expensive car go through. Well, it's not clear because maybe the guy in the expensive car knows more of what's going on, and he might say, okay, I know the other car has a limited view over the scene, so let me be more cautious and let me give the priority to the cheaper car. So you see that having to predict each other's behavior when the information is symmetric is essentially a very, very hard problem. In fact, can be traced back to some long-standing problems in control, for which there's no closed form solution. There's no scalable optimization algorithms. Really hard problems. And I believe this is an area that has a lot of applications, and this car scenario is just one funny application. It has a lot of application, and this is something where machine learning has definitely something to offer. When it comes to, for people who are in the wireless area, replace the cars by radio equipment and talk about, for example, coordinating over allocating pilots or frequencies, beams, caching, power control, and so on. Okay, just to put it in a nutshell, what you're dealing with here is a decentralized decision problem where there is certain environment, which is represent variable X, and you have a number of decision makers. However, each decision maker has only access to an estimate of the environment data, which is X hat and XK hat here for the last one. And you're looking for good policies such that at the output of each policy, the set of actions work well together to give you the highest possible utility. So you're left with having to optimize such a function across all policies at all agents here. And that's the problem, which is inherently a difficult one, as I was mentioning before. So what we looked at in my group a couple of years ago is a machine learning approach to this problem, because after all, machine learning is a great solution for problems that don't have a nice mathematical structure, for which you don't know, scalable algorithms, or you don't have closed form solutions, and for which you have data. And in all these cases, usually with networks, these are cases where you do have a lot of data, and for which the math is almost intractable in this particular case. So this is a great terrain of attack for machine learning. And this is my last slide. I just want to show a little bit the concept of what we propose here. This is called team DNN. The idea consists in using a machine learning solution at each one of the agents, typically exemplified by a neural network here. And these neural networks are trained in order to coordinate with each other in the face of those uncertain information that they are dealing with. So how do you do that? Well, the trick is all in the training part. The training part is done in a way that assumes that the training data is centralized somehow. It's very important, because if you are not able to train to coordinate using centralized data, it's very hard to actually see whether your decisions do lead to a good network performance or not. So it's important during the training stage to have some training data that is centralized. So X is actually made available during the training part, along with the noisy partial data that each decision maker has access to. So the X hat. During the training stage,
I'm sorry to interrupt. I think we need to be wrapping up soon because we're getting to the hour, just to let you know.
Yeah. So this is my last line. So you train them to coordinate together. And once they are trained together, we've shown in a number of examples that in the testing stage, you can feed them with the distributed data, and they will learn to cope with each other's uncertainties. So I just listed a couple of papers here. We looked at, for example, at power control. We looked at beam selection for MIMO. and other examples. So I just want to mention it, and it potentially could be of use in problems dealing with energy, including wireless power transfer, I think. I stop here.
Thank you very much, David, and thanks for making it in such last minute. And you also made slides. This is fantastic, and it's too bad we don't have much more time. I very much like the football analogy. I mean, you know, this thing. When you go watch a football game or a basketball game, which we haven't been doing in a while these days, you realize that what you don't see on TV so much, which is the coach that actually runs back and forth very close to where the ball is and shouts towards his players. And you know, of course, that is some kind of local centralization that he's trying to do. And of course, it's not allowed. He's not allowed to speak to them, you know, via headset or something. So the analogy is of being kind of semi-blind there, because you don't know what happens in another part of the court, I think applies very much. If I could try to, you know, to summarize or to provide some conclusion from all that we heard today, and I think we heard, you know, incredibly insightful comments by all of you, is that the way it seems, I mean, networks will be becoming more and more complex as we'll be, you know, going into the future. There's going to be many more paradigms. There's going to be much more complexity, and there's going to be much higher scale. And also, there's going to be many more tasks to be doing by the network. And there's also seems to be a convergence between, you know, the power grid and let's say the communication network. That's something that you know, is going to be happening more and more. And you know, the whole machine learning aspect, and especially the reinforcement learning, offers a new angle, not only on optimizing things in better ways, but in causing actions that were not perhaps possible before. But in my opinion, you know, adding in this angle comes with a lot of burden. It comes, at least for now, a lot of burden on the computational aspect, on the information exchange aspect, for the training and the learning, and on the energy aspect as well, that it needs to be taken into account, in my view. So the way I see it, if I try to integrate, you know, all the three talks that you guys gave, you know, the future looks like it should be taken into account all the angles. The domains will be merging, and the optimization will be becoming more and more complex, and somehow we're going to have to find ways to deal with it.